Hello everyone, I am Professor Anishwara and I welcome you all in our new series of video lecture. As you all know that currently we are running a course on design of three-phase induction motor, and today we will study or will design squirrel cage induction motor, the rotor of the squirrel cage induction motor. So in today's design numerical, we'll design area of rotor bar and area of end ring. In case of squirrel cage induction motor, we know that we have a rotor and rotor bars. At the outer periphery of the rotor core, we have provided rotor bars. So area of the rotor bar we have to find out, and all the bars are short circuited on both the side with the end rings. So we need to find out the area of the end ring also. In case of squirrel cage type of rotor of three-phase induction motor, rotor resistance is very important because rotor resistance decide the performance of the three-phase induction motor in terms of starting torque as well as efficiency. Because if rotor resistance is more, we have more copper losses and efficiency will be less, but at the same time starting torque will be higher if resistance is high, and opposite is also applicable, meaning is if resistance is low, starting torque is less, but at the same time efficiency will improve. So design of rotor circuit in case of squirrel cage type, that is a rotor bar as well as end ring, that is very important. Let us take one very simple numerical. Suppose data given data, that is suppose 22 kilowatt, 3 phase, 50 hertz, 4 pole, 415 volt, star connected induction motor. Other data which is given is total number of slots, stator slots 48, conductor per slot, that is given 20, number of rotor bars, that is given 55, efficiency, that is 88%, power factor 0.89 lagging, current density in rotor bar as well as in end ring, that is given as 6 ampere per millimeter square. And one more condition is given, that rotor MMF is 0.85 times stator MMF. So 85% of the stator MMF is required for the rotor as a rotor MMF. So what we need to calculate is, we need to calculate area of rotor bar as well as we need to calculate area of end ring. So these two parameters we need to calculate. So some of the steps are very common. Normally we follow in each numerical of design. So we have been given values rating in kilowatt. So first of all we need to convert. So this is our step number 1. Step 1, calculate kVA rating. So that is Q. First of all we will find kVA rating. So in case of calculation of kVA rating in Q, we know that it is a kilowatt divided by efficiency and power factor. So 22 kilowatt, 0.88, that is our efficiency, and 0.89, that is our power factor, and therefore Q is, so 22 divided by 0.88 divided by 0.89, and then it comes to 28.08 or 28.09 kVA. So one of the quantity we have calculated. So 28.09, that is our Q. Now from the kVA rating we can easily able to calculate our stator current. While calculating our bar current, we know that in equation we require our stator current per phase. So for stator current, now we have another equation, that is 3 stator current per phase, stator voltage per phase, stator current per phase, and multiplied by 10 raised to minus 3. See, now one step very important at this stage, that is a stator voltage per phase. Now because it is given that it is star connected, the rotor stator is star connected, it is given, and therefore Vs, that is 1 upon root 3 times line voltage. Phase voltage is 1 upon root 3 times, so, and therefore that is 415 divided by root 3. So it comes to 415 divided by root 3. So it comes to 239.60. So Vs, that is 239.60 volt. This is very important. While calculating the stator current, we must check that whether stator is connected in delta or star. Accordingly, we have to take our voltage. So now from the equation, we can easily able to calculate our stator current per phase. So Q divided by 3 stator voltage per phase and multiplied by 10 raised to minus 3. So 28.09 divided by 3 multiplied by, now phase voltage, that is 239.60 and multiplied by 10 raised to minus 3. So Is, that is stator current per phase, and now 28.09 multiplied by 1000 divided by 3 divided by 239.6, then it comes to 39.07 or 39.08. So 39.08 ampere. So now we have calculated stator current. Now we proceed to our step number 2. So step number 2. Step 2. In step 2, we'll able to calculate rotor bar current. In first step, we have calculated our stator current. Now in step 2 we will able to calculate rotor bar current. Now one condition is given that rotor MMF, that is 85% to stator MMF. Therefore, we apply this equation for bar current IB, that is 0.85 times multiplied by 6 IS TS and divided by SR. So now importance of two parameters. One is SR, that is a rotor slot. Rotor slots are directly not given, but rotor number of bars are given. So number of rotor bars are exactly equal to the number of rotor slots, and that is given. We have been given 55. So rotor number of slots 55. Stator number of slots given, that is 48. Now rotor slots is given, that is 55. So one of the quantities we have calculated. Another quantity, that is total number of stator turns per phase. So some of the parameters we have been given. Total number of slots, that is 48, and conductor per slot is given 20. So total number of conductor, that is ZS, that is 48 multiplied by 20. So it comes to 48 multiplied by 20 and 960. So it is 960. So we have calculated our total number of conductor. Once total number of conductor if we have, then based on this value we can easily able to calculate our stator number of turns per phase. So we have ZS, that is 6 times stator number of turns per phase. This equation we know, and therefore stator turns per phase, that is ZS, that is total number of stator conductor divided by 6. So 960 divided by 6, and therefore TS, that is 960 divided by 6, that comes to 160. So 160. So another parameters which was not known, that also we have calculated. So now IS and TS, both the values we have. So now again, as per the equation of bar current IB, that is 0.85 multiplied by 6 IS TS and divided by SR. So now let us substitute all the values. So 6 multiplied by IS, that is stator current 39.08, TS, that is stator number of turns per phase, that is 160, and divided by SR, that is 55. So bar current we have. So let us calculate 0.85 multiplied by 6 multiplied by 39.08 multiplied by 160 and divided by 55. So it comes to 579.80. 579.80 ampere. So IB we have calculated. So it comes to 579.80. So let us proceed to our step number 3, right? As we have calculated bar current, same way we can able to calculate in step 3, that is calculate end ring current. If both the currents are available, then based on the current density, we easily calculate area of end ring as well as area of rotor bar. So calculate end ring current. That is IE. Now we have another equation for end ring current. It is IE. That is SR. That is rotor number of slots divided by pi P and multiplied by IB. IB is rotor bar current. Now again in this equation, one quantity is not available, or that is available rather, that is number of P. Number of P is given 4. Okay. So 55, 3.14 multiplied by 4 multiplied by IB. IB is a bar current. So IB we have just calculated, it is 579.80, and therefore IE is equal to, so 579.80 multiplied by 55 divided by 4 divided by 3.14. So it comes to 2538.93. 2538.93. So this is our end ring current, ampere, right? So another quantity we have calculated. In step 1 we have calculated stator current. Based on the stator current, in second step we have calculated rotor bar current. Based on the rotor bar current, in step 3 we have calculated our end ring current. Now the last step, that is step number 4. So in step number 4 we will able to calculate area. Step 4, calculate area of rotor bar and end ring. So current density is given. Say normally we use the equation, general equation, that is current density, that is current divided by area, cross section area. So based on this equation, now first we calculate area, and therefore area is equal to I divided by current density. So we use this equation, right? So first we calculate area of the bar current, area of the rotor bar. So IB divided by delta, that is current density. IB we know that it is a 579.80. Current density, that is given 6 ampere per millimeter square. If it is not given, we can always assume appropriate value of the current density, but now it is given, so it is 6, and therefore area of the rotor bar, that is 579.80 divided by 6. So it comes to 96.63 millimeter square. Current density is in ampere per millimeter square, so area will come into millimeter square. Same way, area of the end ring, that is end ring current divided by current density. End ring current, that is 2538.93, and again 6 current density is given, and therefore area of end ring current, that is 2538.93 divided by 6. So it comes to 423.15. 423.15 again millimeter square. So both the quantities we have calculated. So in stator design, in case of squirrel cage induction motor, we have only 3 quantities, that is a number of rotor slots, then area of the rotor bar, and area of the end ring current. So it is very simple. If we go step by step, if we follow all the steps, then it is very easy to design a squirrel cage rotor. Thank you for watching my video. Keep watching my video. Thank you very much.